Welcome to today's video lesson. So today we're switching gears from what we were in the half of the unit that we were in before was called thermochemistry. And now we're in the second part of the unit, which is called thermodynamics. And thermodynamics is used to predict whether a certain reaction will occur or not. Before we go into sort of like today's sort of like introduction lesson, let's talk about sort of like what we've done and what we're going to do. So we started off the year with stoichiometry, which deals with calculating how much product will be made or how much reactant is needed. Then we took a segue into gas laws with our little favorite thing, ideal gas law, PV equals nRT. And then we took a unit about chemical reactions and solution stoichiometry, which we really asked the question, how can we predict the products? What is going to be made in a chemical reaction? Then we learned electrochemistry, which is all about galvanic cells and the production of energy, or the using of energy to complete a task by transferring electrons. And we just finished our quiz on thermochemistry, which is essentially about heat released the heat that's either released or absorbed by reactions or processes. Okay, and now we're in the thermodynamics section of the course, which really predicts whether or not reactions will occur. Okay, and if they will, at what temperature are they likely to occur? Okay, some reactions need warm temperatures, some reactions need cold temperatures. That's sort of the goal of the rest of the learning until Christmas, is to figure out what determines whether reactions will occur or at all. When we get back from Christmas, that's the halfway point. So this year is sort of like the halfway point of the course. When we get back from Christmas, we have 5 more units to learn. One is equilibrium, okay, which discusses whether a reaction will occur completely. Sometimes we've done reactions, we assume all the reactants get turned into products, and that's not true. Then we're going to talk about kinetics, okay, which discusses if a reaction is going to occur, and we know how much it's going to occur, or how much is going to be turned into products, how fast will the reaction occur? Which is, if you remember for AP students, a little bit very similar to what we learned like with enzymes and which affects enzyme rate. And then the last 3 units are acid-base chemistry, which is going to be really annoying, atomic structure and periodic trends, which we learned as 10th graders, and then bonding and intermolecular forces. So that is sort of where we are in the course right now. But let's sort of begin thermodynamics now. Actually, before we start, take a step back. And so in terms of chemical reactions, what we have left to learn, okay, is predicting whether a reaction will occur. Okay, and then if we know it occurs, will it occur completely? Will all the reactants be turned into products? And then lastly, with chemical reactions, we have to learn how fast, what determines how fast a reaction will occur. So that's what's left to learn about chemical reactions. Okay, so we have this word spontaneity, which refers to the fact that every process or every reaction has a preferred direction under a given set of conditions. Okay, so if we look at a reaction, which one is going to pop up, okay, a process is said to be spontaneous, okay, if it's going to occur, and no outside intervention needs to occur once the process gets started, okay. If you want to reverse a process that's spontaneous, you have to input some sort of energy to reverse the reaction. So if we're looking at this reaction here, we're asking, okay, well, if you had, let's say, equal amounts of A and B, let's say you had 1 mole of A and 1 mole of B, and 1 mole of C and 1 mole of D, which way is the reaction going to occur? Or which way is the reaction spontaneous? Would it prefer to go this way and make A and B, or would it prefer to go this way to make C and D? Okay, and that depends on various conditions. Okay, when a reaction is favorable, meaning it's going to occur, we call that reaction thermodynamically favored. But one caveat to this is that most reactions that are even spontaneous, okay, require some amount of activation energy, which we're going to talk much more when we get into kinetics. So like, for example, if you have water that flows down a dam and there's a gate, okay, the activation there would be opening the gate. Once you open the gate, that water is spontaneously going to flow down into the dam. Okay? Another example is combustion, right? If 2 things are going to combust, right, you need to spark them to get them to ignite. So like, for example, that's why I tell you not to like open flames by gasoline or smoke at a gas station, because that spark could ignite the gasoline on fire. Okay, but once you provide that spark, if it's enough, right, the reaction will occur, or the reaction will be spontaneous. So if we take this idea of spontaneity, or thermodynamically favorable reactions, in terms of what we just learned, in terms of endothermic and exothermic reactions, the reactions that tend to be spontaneous are the ones that are exothermic, and remember that means that delta H is negative, okay? And the reason why these are more likely to be spontaneous is you generally don't need to provide energy for them to occur, okay? They release energy. So, from the previous unit, reactions that are exothermic tend to be more thermodynamically favorable than ones that are endothermic, okay? That does not mean that endothermic reactions don't occur, okay? They can be thermodynamically favorable, okay? But exothermic reactions are more likely to be thermodynamically favorable. There's another factor that affects whether a reaction is spontaneous or thermodynamically favorable. And we're about to discuss this a factor right now, and then in more detail on Friday. So, there's this sort of common sense law, which is actually called the second law of thermodynamics, which states that things tend to become more disperse. Or the other way of saying is that things tend towards disorder. If you look at my classroom, you can see that it definitely does not lead towards order. Okay, so examples of this, like if you have marbles, okay, you can roll them out of the bag and they can scatter around the room, but they're not very likely to roll back into the bag. If a fence falls down, okay, it can fall down, but it's not likely that the piles of wood are going to assemble back into a fence. And then sort of the last example with jigsaw puzzles, like if you throw the jigsaw puzzle on the floor, it's likely to scatter into a million pieces, okay, but it's not going to be very easily reassembled without any input of energy. Okay? So, reactions that tend to be thermodynamically favored tend to increase disorder. Okay? Reactions like to proceed in a way that reduces constraints or makes there be more possibilities of way things can align. Okay? So, in summary, reactions that are thermodynamically favorable tend to increase disorder. Okay. Now, we have a word for this disorder, and that is called entropy, okay, and is given the sign delta S, okay? And delta S is a measure of disorder, okay? And, you're not going to like this, okay? If a process makes something become more disordered, okay, delta S is positive, okay? And I think about that, I remember that because I think about my life, and my life is like very disordered, and that's just the way it is, and I actually think disorder is a positive thing. It's more fun than order. So that's how I sort of think about that. Now, if the process makes something become more ordered, okay, or less disordered, delta S is negative. Friday in class, we're going to discuss sort of reactions and whether or not they're increasing disorder or decreasing disorder. Okay, now, last part of this is there are two things that determine whether a reaction is spontaneous or thermodynamically favorable. Okay, the first one, and there he is, our good friend Bolton, okay, is driven by enthalpy. Okay, so reactions can be thermodynamically favorable, okay, if they're exothermic, or energy is released. So that's one thing that determines whether a reaction is likely to be spontaneous. Okay, the other thing, okay, is whether or not the reaction increases disorder. Okay, so reactions that increase disorder or increase entropy or have a positive delta S also tend to be spontaneous. Okay, we are going to see both of these drive reactions. Okay, we're going to see how they affect each other because they do next week. Okay, but for now, you need to know that reactions that tend to be spontaneous, as our good friend Bolton, okay, is telling you, okay, are ones that release energy, okay, or like lower the amount of energy in the products, okay. That means they're exothermic, or end reactions, okay, that increase disorder, or have a positive delta S, or increase entropy. Okay, tomorrow in class we're going to discuss what type of reactions increase entropy, and which type of reactions decrease entropy. And then on Friday, on next week, we're going to put these two together, delta H and delta S, and determine how do we know, based on these values, whether or not a reaction is going to occur, whether the reaction is going to be spontaneous, or whether the reaction is thermodynamically favorable. All those things mean the same thing. Go answer the guided questions. Have a good Thursday.